A wooden box mounted on your south-facing wall, painted black inside, covered with clear polycarbonate, with two holes drilled through the siding, one at the bottom and one at the top, eliminates 40 to 60% of your heating bill forever. No electricity, no gas, no moving parts, just sunlight heating air to 140 degrees and flowing it directly into your home through a passive convection loop that runs itself. $50 in materials, one afternoon of work, and every heating bill you have paid for the last decade could have been cut in half. In 1881, a zoologist who had been expelled from nearly every school he attended filed a patent for a device he called a sun heater. Edward Sylvester Morse was studying seashells in Japan when he noticed Japanese homes stayed warm in winter without burning fuel. He documented the principle, returned to America, and patented a glass-covered box that captured sunlight, converted it to heat, and circulated warm air through a room using nothing but the temperature difference between hot and cold air. NASA uses this exact principle to heat facilities at the Kennedy Space Center. The United States military uses it at Fort Drum in upstate New York, where January temperatures drop to minus 20 degrees. Ford Motor Company installed 200,000 square feet of it on assembly plants in Ontario. FedEx uses it on distribution centers across North America. And the $120 billion residential HVAC industry has spent over a century making absolutely certain you never learned the two words solar air heating. They did not stop promoting it because it failed. They stopped promoting it because a $50 wooden box with no service contract, no replacement parts, and no monthly utility bill makes an entire category of recurring revenue permanently unnecessary. Stay with me until the end because the last detail is a technique I found still in use inside Mennonite homes in Holmes County, Ohio, that I have never seen documented in any modern solar heating guide. The average American household spends between $1,200 and $3,000 per year on heating, depending on climate and fuel type. Over a decade, that is $12,000 to $30,000. Over 30 years of homeownership, that is $36,000 to $90,000 flowing straight to utility companies and HVAC contractors for a service the sun provides for free every single day. A properly sized solar air heater mounted on a south-facing wall offsets 40 to 60% of that total heating load. $40 in lumber and polycarbonate versus $60,000 in heating bills. That is not a difference in cost. That is a suppression of knowledge so complete that most homeowners have never encountered the phrase passive solar air heating in their entire lives. The history of solar air heating begins not in a laboratory, but in ancient observation. Roman bathhouses used south-facing glass windows to trap solar heat and warm interior spaces as early as the 1st century CE. Persian architecture documented the use of dark masonry walls behind glass or translucent screens to capture and store solar heat throughout the winter. Chinese builders used south-facing paper screens over dark interior walls to passively heat living quarters without fuel for over 1,000 years. Different civilizations separated by continents and centuries independently converged on the same principle. A dark surface absorbs sunlight and converts it to heat. A transparent barrier traps that heat by allowing light in while preventing warm air from escaping. Hot air rises naturally, pulling cooler air from below into the heated space and creating a self-sustaining convection loop. That loop requires no fan, no pump, no electricity. It runs on the temperature difference between warm air and cool air, a principle physicists call a thermosiphon. In 1877, Edward Sylvester Morse, a zoologist and professor at the Peabody Academy of Science in Salem, Massachusetts, traveled to Japan to study brachiopods, small, ancient shelled creatures. Morse had been expelled from multiple schools as a child. He never earned a formal degree, but he possessed an obsessive eye for observation. When he arrived in Japan and traveled through the countryside in winter, he noticed Japanese homes oriented deliberately toward the sun, with south-facing walls built from dark surfaces and covered with translucent paper screens. Morse walked into these rooms expecting to shiver. Instead, the air near the walls was warm, measurably warm. There was no fire, nothing was burning. The sun was doing all the work. Morse understood immediately what he was witnessing. The dark wall absorbed sunlight and converted it to heat. The translucent screen trapped that heat. Hot air rose, pulling cooler air from below into the space and creating a continuous, self-sustaining cycle. The Japanese had not invented a machine. They had observed a law of physics and built a wall around it. Morse returned to America obsessed with translating this principle into a device any American homeowner could build. On April 5, 1881, the United States Patent Office granted him patent number 239767 for a solar air heater. The design was devastatingly simple: a glass-covered box mounted on the south wall of a building with a dark interior surface to absorb sunlight. At the top, a vent to let hot air flow into the room. At the bottom, a vent to pull cool room air back into the collector. The air circulated by itself, no fans, no fuel. The device powered itself through convection. Morse had created a furnace that required no combustion and no recurring cost. So why is this invention not on every house in America? Timing. Morse filed his patent at the exact moment the United States was building a fossil fuel empire. The sheer energy density of coal and oil and the fortunes being made by the men who sold them totally eclipsed a quiet wooden box on a wall that could not be metered, could not generate licensing fees, and could not produce recurring revenue. When Morse's patent expired, it entered the public domain. Anyone could build it for free. That made it the last thing a fuel company would ever want you to discover. Mennonite builders in Lancaster County, Pennsylvania, and Elkhart County, Indiana, never stopped using this principle. While the mainstream construction industry spent the 20th century burying passive solar air heating behind the explosive growth of oil furnaces and electric baseboard heat, Mennonite carpenters kept building south-facing overhangs, dark interior masonry walls, and glazed wooden boxes that fed warm air into workshops, barns, and living spaces without burning a single gallon of fuel. I visited a Mennonite farm outside Napanee, Indiana, where a master builder named David showed me a workshop he constructed in 1996 with a 12-foot wide solar air collector mounted vertically on the south wall. The collector is nothing more than a wooden frame, a sheet of salvaged tempered glass, and a black painted aluminum screen inside. 2 4-inch holes drilled through the wall, one at the bottom and one at the top. On a sunny January morning with an outdoor temperature of 18 degrees, the air exiting the top vent into the workshop measured 134 degrees. I held a thermometer in the output vent myself. David told me something I have not been able to stop thinking about. He said his grandfather built the first one in 1952 after reading about Edward Morse's patent in an old engineering journal. His family has been building them on every structure they own for 70 years. He has never paid a heating bill for his workshop, not once in 3 decades. For 80 years after Morse's patent, the principle gathered dust while the fossil fuel industry roared forward, conditioning entire generations to believe that warmth in winter required a monthly payment. Then, in 1964, high in the French Pyrenees, 2 men quietly picked up where Morse left off. Félix Trom was a physicist. Jacques Michel was an architect. They worked at a solar research facility originally designed to melt metal with concentrated sunlight. They had a different question. Could that same free solar energy sustain human life in a freezing mountain climate? They identified Morse's one critical weakness. His panel worked brilliantly while the sun was shining, but the moment the sun set, the heat stopped. For a home in the mountains where the most dangerous cold comes after dark, this was a fatal flaw. Their solution was elegant. Instead of heating air directly, they placed a solid masonry wall, thick concrete or brick, sometimes 12 inches deep, painted dark on the exterior side, directly behind a sheet of glass with a small air gap between. This changed everything. Concrete is extraordinarily dense. It absorbs heat slowly and releases heat slowly. A 12-inch concrete wall behind glass would soak up solar energy all day, taking 8 to 10 hours for the heat to conduct all the way through the material. That time lag meant something extraordinary. Right when the sun set and the mountain air turned lethal, the inner face of the wall began radiating its stored warmth directly into the living space. The sun went down, the wall kept heating for 8 to 12 hours through the night. This became known worldwide as the Trombe Wall.
Trome and Michel documented that this simple glass and masonry system met 30 to 45% of total heating demand in a climate at 6,000 feet of elevation. Their results were peer-reviewed, replicated, and published. They had proven that you did not just have to capture solar heat, you could store it without batteries, without chemicals, without a utility company. The physics are worth understanding because they reveal something the modern energy industry would prefer you never think about too carefully. Every home you have ever lived in already contains thermal mass, concrete foundations, brick walls, tile floors. These materials absorb and release heat all the time. Nobody designed your house to harness that process because nobody in the supply chain profits from it. In 1973, the global oil crisis hit. Fuel prices skyrocketed, and for a brief moment, America was forced to ask a question it had been avoiding for a century. What if there is another way? People started building. In New Mexico, a self-taught solar engineer named Steve Baer began constructing homes heated entirely by 55-gallon drums filled with water, stacked behind south-facing glass walls. Water absorbs heat even more efficiently than concrete. Baer's drum walls kept entire houses warm through freezing desert nights. He had independently arrived at the exact same principle as Morse and Trombe, a century of reinvention because the original knowledge had been allowed to disappear. At the same time, physicist Doug Balcom at Los Alamos National Laboratory launched the most rigorous study of passive solar heating ever conducted in the United States. His team tested glazed collectors across multiple American climate zones. The data was unambiguous. A properly sized south-facing solar air heater could meet 30 to 70% of a building's heating needs. No fuel, no moving parts. The Department of Energy published the results. For about 5 years, it looked like the American home was about to be reinvented. Then the political wind shifted. Between 1980 and 1985, federal solar research funding was slashed by 89%. The Los Alamos Passive Solar Program was gutted. Tax credits for solar thermal systems were allowed to expire quietly. In less than 5 years, the second wave of American solar heating research was dismantled. It was not dismantled because it failed. The data proved it worked. It was dismantled because the people writing the budget had different priorities shaped by the largest and most powerful lobby in the country. The knowledge was buried again, but the technology did not die. It went underground, adopted only by institutions whose survival depends on cutting costs and eliminating vulnerabilities in their supply chain.
In the 1990s, Canadian engineer John Hollick invented a radical improvement on the original concept. Instead of a glass-covered box, Hollick developed a perforated metal cladding painted dark, mounted on the south wall with a small air gap behind it. He called it the solar wall. The physics are fascinating. Even on a windy day, a microscopic layer of air less than 1 millimeter thick remains completely stationary against the surface of the heated metal. Physicists call this the boundary layer. Using a standard ventilation fan, Hollick's system creates negative pressure behind the panel, sucking this superheated boundary layer air through thousands of tiny perforations before the heat can escape into the atmosphere. Efficiency exceeds 70%. That makes it the most cost-effective solar heating technology on Earth for large buildings. The client list reads like a classified briefing. Ford Motor Company installed 200,000 square feet on assembly plants in Ontario. FedEx uses it on distribution centers. NASA uses it at Kennedy Space Center. The United States military uses it at Fort Drum in upstate New York, where January temperatures plummet to minus 20 degrees Fahrenheit. The Army does not use it because it's trendy. A 40% reduction in a military base's heating bill is a strategic advantage. It reduces dependence on fuel supply chains an enemy can target. Good enough for the Army in sub-zero winters. Good enough for NASA. Good enough for Ford. But somehow not available to you. If you have made it this far, you already know more about passive solar air heating than 99% of licensed HVAC contractors. But stay with me, because what comes next is the part they really do not want you to hear. I need to be honest with you. Solar air heating has real limitations. It only works on south-facing walls with unobstructed sun exposure. If your home faces north or is shaded by trees or buildings, this technology cannot help you. It provides heat only when the sun is shining, unless you add thermal mass storage, which increases complexity and cost. And for climates with sustained cloudy winters, solar air heating offsets a smaller percentage of total heating load. It is not a universal solution. But for what it does, heating air directly from sunlight at nearly zero operating cost, nothing on the market at any price matches it. Here's exactly how to build one. A basic vertical solar air heater requires a wooden frame, a sheet of clear polycarbonate or salvaged tempered glass for glazing, a dark absorber surface inside, and 2 holes drilled through your south-facing wall, one near the floor and one near the ceiling. Total material cost is $40 to $60, depending on what you salvage. For the frame, construct a rectangular box from 2x4s, approximately 4 feet wide by 8 feet tall by 4 inches deep. For the absorber, use aluminum window screen painted with high-temperature flat black paint, or crumpled aluminum cans, or corrugated metal roofing painted black. The key is a dark surface with high surface area that forces air to tumble and make contact as it flows through. For glazing, a 4x8 sheet of twin-wall polycarbonate costs approximately $16 at any hardware store. Tempered glass salvaged from old patio doors works even better if you can source it. Drill a 4-inch intake hole near the floor of your south wall and a 4-inch output hole near the ceiling. Mount the collector box over those holes so the bottom of the collector aligns with the lower hole and the top aligns with the upper hole. Seal all edges with silicone caulk. Install a plastic backdraft damper on the lower vent so cold air does not reverse flow at night. That is the complete system. When the sun hits the dark absorber, it heats to temperatures exceeding 140 degrees. Hot air rises naturally through the top vent into your home, pulling cool room air in through the bottom vent to be heated again, a continuous loop powered entirely by convection. A single 4x8 panel produces between 1,000 and 3,000 BTUs per hour, depending on sun intensity. And that's enough to offset 15 to 25% of your daily heating load. Build 4 panels across your south-facing wall, and you're offsetting 50 to 70% of total heating demand. A vertical south-facing wall is geometrically perfect for winter sun. In winter, the sun hangs low in the sky, hitting your south wall at a steep, direct angle. In summer, when you do not want extra heat, the sun is high overhead, and the same wall receives almost no direct light. The system self-regulates with the seasons. A retired mechanic in Bemidji, Minnesota, built a solar air heater on the south wall of his garage in 2014 using scrap wood and crushed aluminum beer cans. His glazing was a 4x8 sheet of twin-wall polycarbonate for $16. Total materials cost was $37. On a sunny February morning at 10:30 a.m., the output vent was blasting air at 131 degrees into his garage, while the outside temperature was below freezing. His gas bill dropped 40% that winter, $37 versus $600 in heating costs saved annually. Now here's the piece I have never seen in any modern guide. I found it inside a Mennonite home in Holmes County, Ohio, where a carpenter named Amos showed me a technique his family has used for 3 generations on solar collectors. After constructing the standard frame and absorber, they paint the entire interior back wall of the collector box with a mixture of flat black paint and fine sand. The sand creates a rough textured surface with dramatically increased surface area compared to smooth painted wood. Air flowing across that textured surface makes contact with far more heated material, increasing heat transfer efficiency by an estimated 15 to 20%. Amos showed me a collector his father built in 1981 with this sand-textured back wall. I measured the output temperature myself, 147 degrees in a January afternoon with an outdoor temperature of 22 degrees. I searched every passive solar manual, every DIY solar air heater guide I could find. None mention a sand-textured back wall. The Mennonite carpenters in Holmes County have been doing it quietly for decades. Every heating bill you ever paid was never for a service only a utility company could provide. It was for a service the sun provides for free that an entire industry has spent a century making sure you never learn to capture. With $50 of lumber and polycarbonate and 1 afternoon of work, every south-facing wall in your home becomes a furnace that runs itself. Every HVAC invoice you ever received was not a reflection of the technology's complexity. It was a reflection of 100 years of silence around a wooden box that eliminates recurring payments. Tell me in the comments which wall you're going to build on first. Your answers determine what we cover next. Subscribe now because next week we're going deeper into a Mennonite root cellar design that maintains 34 degrees year-round without electricity, and the earth-coupling thermodynamics behind it will change how you think about refrigeration forever. The knowledge was never lost. It was just waiting for someone to remember.